not the best, but from there, I did say, I'm just going to abbreviate it. So C is cosine, S is sine. So this is opposite over adjacent because of SOHCAHTOA, right? TOA, opposite over adjacent. Opposite is referring to sine, adjacent is referring to cosine, right? And then, bam, like that. You would create a complex fraction for things right there. So just give me a second. So if I'm going to create another complex fraction, I'm just going to go ahead and erase this, right? And then I'm going to just write everything I know here. So it'll be 1 plus sine theta all over cosine theta all over 1 minus, and then this is plus sine theta all over cosine theta d theta, the sign there. This is the same, right? So it's just a little bit of a side note. 1 is equal to 1 over 1. There's nothing different about those two. They mean the exact same thing. So over here, when you're adding or subtracting fractions, denominators must be equal. So if I then decide, okay, fine, 1 over, oh, this is horrible. 1 over 1 minus tangent theta, which is the same as I already said, sine theta over cosine theta. You would multiply the reciprocals, so it'd be cosine theta times 1 over here, cosine theta, well really I should take it back, 1 times 1, and then cosine times cosine. So then you would get cosine theta all over cosine theta minus sine theta, and then 1 over 1, this should be sine theta all over cosine theta, making it cosine theta plus sine theta all over cosine theta. Yes? So now, if I just fix everything the way it is, right, and I put everything back to normal, and then I say, okay, so then this is so light, give me a second. Okay, so if I fix everything the way I needed it to, it would be cosine theta minus sine theta all over cosine theta plus sine theta all over cosine theta. The cosine thetas single out, and then again I am now left with cosine theta plus sine theta, and then always you need to have your d thetas. Now, you might say, what am I going to do from here? This seems invariably impossible to solve. Man, what is this? And I'm going to tell you, well, this is this. I'm going to say u is equal to cosine theta plus sine theta, like that. Then I'm going to say du is equal to, what is the derivative of each one respectively? For cosine, it's just negative sine theta. For sine, it's cosine theta. That's the same as this. And then the d theta, right? You got to have the d theta there. D theta right there. So then you go du all over cosine theta minus sine theta is equal to d theta, and you bring it over here, then I can just literally rewrite everything. I can say this is just u. I said d theta was du all over cosine theta minus sine theta. These cancel out, so then I'm left with u to the negative 1 du, which is just ln, and then I'm going to abbreviate c for cosine and s for sine, c plus well, if you want to be more and more in depth, ln of u plus c, which implies ln of c plus s plus c. And that's how you solve that one. Boom, boom. Now this one is one that many of you guys got duped on. This one and the third one. Most we didn't even get to the third one. But we're going to get there. So, take a look, see. It's not that crazy. I can break this down into radical tangent theta d theta times 2 cosine theta sine theta. Okay? They equate, the new denominators mean the same exact thing. So I'm going to do something a little unconventional. I'm going to say u is equal to tangent theta. So then du is equal to secant squared theta d theta. That should be a squared and not a 3. So then I say du is equal to secant squared under its denominator, which equals d theta. So du over secant squared theta is equal to d theta. Okay? So, radical u, and then what I have for d theta, secant squared, and then I'm going to take out the 1/2 here, cosine sine. Right? Do we see how we got from here to here? Simple u substitution. I know that cosine is equal to 1 over secant theta. Same way that sine is equal to 1 over cosecant. Same way as tangent equal to 1 over cotangent, etc. This is the same as this. 1/2 times radical u cosine theta sine theta times 1 all over secant squared theta times du. If you squared this, it's the same as this, because this and that equate. 1 over secant squared theta is equal to 1 over secant squared theta. Well, sorry, 1 over secant squared, like all that together, is equal to 1 over secant squared theta. Because 1 is equal to itself squared, not that crazy. It doesn't always work though. So, and then you have this. Okay? So that's the same as doing this. 1/2 radical u cosine squared du all over cosine theta sine theta. These thetas cancel out, and then you're just left with 1/2 radical u cosine theta sine theta du. I previously mentioned this. Tan theta is equal to 1 over cotangent theta. And I said this is equal to u. So, in turn, cotangent theta is equal to 1 over u. Just ignore that for a minute. Cotangent theta is equal to 1 over u. Okay? Does that make sense? So, from here, if I just move everything this way, I would get 1/2 radical u, and then I have cosine over sine is equal to cotangent theta. It's the opposite of tangent theta. Opposite over adjacent, adjacent over opposite. Okay? And I say that is equal to 1 over u. So it'd be 1 over u times du. It'd be radical u over u, 1/2, the integral and everything like that. I'm going to go ahead and erase this part right here, because I don't need it anymore. That's just u to the 1/2 power all over negative u, so 1 minus 1/2 would get you 1/2, and then this will be u to the negative 1/2 du, which is just u to the 1/2 2 times a half, right? And then you would get literally radical tangent theta plus c. That's your answer for this one. Stay strong, guys. This next one. Cosecant squared theta, cotangent squared theta, all over radical cotangent squared theta minus 17. First thing I'd recommend you guys doing is I'd recommend you guys substitute using your u substitution. So u is equal to cotangent theta du is equal to negative cosecant theta squared with the d theta right here. When you make d theta go by itself, it's just du over cosecant squared theta. So with this newfound knowledge, it'll be cosecant squared theta u squared du all over negative cosecant squared theta times u squared minus 17. Simplify all this, you're left with just negative u squared du u squared minus 17 with that in the radical. You're going to use trigonometric substitution here. Alright, so I like to use a triangle because it makes my life easy. And I don't really have to do too much thinking. That's all I care about here. I know for a fact that this is the hypotenuse, so u. I know for a fact that this looks a lot like an identity that I'm aware of, which is secant. The main bases as to when to choose specific ones, you're going to want to substitute any x over a, tangent x over a, sine x over a. The way you want to substitute it is that it fits in this format for every single one of your substitutions. It doesn't matter which one is going to be appropriate for when you solve your problem, but when you solve your problem, it must fit so that it's x over a always. And this cheat sheet will help you out indefinitely. This is the kind of formats you need to pay attention to. Radical x squared minus a squared, radical x squared plus a squared, radical a squared minus x squared. Fits for all those. It also works without the radicals. I just like to add the radicals. So technically the correct way, 2 and 2, technically the correct way is like this. 2 and 2 like that. Yeah? Does that make sense? Perfect. So based on what we have here, the closest one is actually the first one, secant. Okay? So then I say, from here, I go, okay, my x is there, my u is there. Secant is hypotenuse over adjacent. That's why I knew x, or in this case u, was my hypotenuse. My adjacent is a, so that's radical 17. And my side is that. If I just went ahead and substituted everything, just erase this down here, I know that secant theta is just u over radical 17, implying radical 17 secant theta is equal to u. So radical 17 of secant theta tangent theta d theta is equal to du. Okay? I'll worry about that triangle when I get there. I'm not too crazy about it anyway. So u squared is 17 secant theta because of the squared up there. Du, I said, was radical 17 secant theta tangent theta d d theta. Transform everything to thetas again. I know these are in thetas. You have to technically put them in different ones because we already have thetas, but I'm so used to theta that I don't particularly care. But your professor will get mad at you for it. Radical here, again, I said 17 secant squared theta minus 17. You'll get these out of the way. It'll be a radical 17 in there. So when you get these out of the way, this gets out of the way. So then you're going to get radical secant squared minus 1, which is the same as tangent. So then you're going to get this one out of the way. So then you're going to get 17 secant squared times secant, like that. And there's no all over 1 because it's already just by itself, so you don't have to really write that again. Okay? So we're there. When you simplify everything, this just indubitably means that this is 17, there's a negative in here, I haven't forgotten, times secant cubed theta d theta. It shouldn't be theta, but I'm just so used to theta that I write theta. So for me, and for your sake, don't write it in the way that I wrote it. Write it with a different variable, write like p or something like that. So secant squared secant d theta. This is where you're going to use integration by parts. U is equal to secant theta, du is equal to secant squared theta, dv is equal to secant squared theta, v is equal to tangent theta. So again, you'll be like, oh, my bad. This is going to be secant theta tangent theta. So then you're going to have integral of secant cube theta times 17, right? That's out there or whatever. I'll worry about that when I get there. I'm just treating it in terms of like this. So u secant tangent minus what I have, which is secant squared, secant tangent times tangent, which is secant times tangent squared. So d theta. I'm going to create what I know here as secant squared minus 1. That's what tangent squared is equal to. Again, because 1 plus tangent squared is equal to secant squared, therefore secant squared minus 1 is equal to tangent squared. Okay? So this becomes another secant cubed right here when you add this. And then this just becomes secant theta, which when I add this over to the other side, makes this 2 secant cubed theta d theta, which is equal to secant theta tangent theta plus ln of secant theta plus tangent theta. I divide this by 2 times 2, so then it would just be all divided by 2. But I had a negative 17, right? That negative 17 didn't disappear on me. What happened was I just didn't count it at the time. So it's literally negative 17 times 2 secant theta tangent theta plus ln secant theta plus tangent theta plus c. But I'm not done because I got to convert everything back into their respective values, which I said with the triangle u squared minus 17 radical and then 17 radicalized. Okay, I said secant was u over radical 17. I said tangent was opposite over adjacent. This makes this product 17 down here, and this makes u just cosecant theta. All the while this makes that radical cosecant squared theta minus 17 plus ln radical 17 cosecant theta. Oh, did I say cosecant? I meant cotangent. Cotangent theta, cotangent theta, cotangent theta. And over here, this is cotangent theta plus radical cotangent theta squared minus 17 plus c. And that is how you get that. So there you go.